In this video, we will use reinforcement learning to convert small language models into powerful reasoning networks that can think step by step to solve complex logical tasks. You must have seen reasoning models by now. DeepSeek, Google, OpenAI, Anthropic, practically everyone other than Apple are releasing a new reasoning model every month. And when you ask a question to these models, they first generate a chain of thought and then generate an answer. Reasoning can drastically improve the accuracy of language models on many math and logical tasks. And today, we will teach this behavior to really small models, like only 135 million parameter models. And that's more than 1,000 times smaller than GPT-3. And I don't even know how much smaller than GPT-4. Specifically, we will write a reinforcement learning algorithm called GRPO from scratch to teach SLMs how to reason and generate accurate answers more often. If this is the first time that you're hearing the term GRPO, this is the same algorithm that the researchers over at DeepSeek used to train the seminal DeepSeek R1 models. When I started on this project, I thought that it was going to be easy. But boy, was I wrong. This turned out to be one of the hardest projects that I've worked on for this channel. Deep reinforcement learning is finicky and sensitive to implementation details as well as hyperparameters. And SLMs are even more finicky because they simply don't have the world knowledge of the larger models. I had to dig through multiple papers, read open source code, burn through most of my GPU credits until finally I understood things well enough to actually hit that record button. In this video, I will break down all of the concepts that I learned step by step and provide a simple recipe that should allow you to train your own reasoning networks for your use cases in just $5 to $6 of cloud GPU resources. First, we will look at how to generate task simulations for doing text-based RL. Next, I will visually explain how GRPO works, all the components, and do a deep dive into the policy gradient equation. This equation is at the heart of our implementation, and although it may look big and scary right now, this is going to become very easy and you'll understand it like the back of your hand. Third, we will look at some code about how to actually implement GRPO from scratch. And fourth, we will learn about supervised fine-tuning and look at some results. Finally, in chapter 5, I'll give you 10 key points that really goes into the weeds of hyperparameter optimization and implementation details that no other walkthrough that I found have gone into for training reasoning into small models. And this final section is especially useful for folks who are not looking to implement the algorithm from scratch and instead want to learn how to pick configurations and hyperparameters with external libraries like TRL, verifiers, unsloth, and so on. I work on random deep learning projects all the time, and if you want to follow along the journey of my next big project, come follow me on my Twitter. All the materials that I have presented in this video will be shared on my Patreon page. It helps me to pay my bills and work on content like this. So 100% please go check out my Patreon page. If you enjoy this content, don't forget to hit the like button and leave a comment because that helps the channel in a massive way. Awesome. And with that, let's get back into the video. So to do RL, we first need tasks. In this video, for the sake of simplicity, I'm going to pick two simple but kind of complicated tasks to understand and fine-tune reasoning models. Let's see how one of the tasks called syllogism looks like. A syllogism task is a type of logical puzzle designed to test deductive reasoning. Basically, we will provide the LLM two premises and ask if a conclusion is correct or not. The LLM is supposed to reason by considering both the premises and then finally generate a yes or no answer to tell us if it thinks the conclusion was correct. Our second task is the propositional logic task. It's a symbolic reasoning task where the LLM is provided with some symbols and asked to generate conclusions. Unlike syllogism, this is not a yes or no binary task. Instead, they have to generate the correct conclusion. And that makes this task considerably harder than syllogism. In this video, we are using the Reasoning Gym library. Reasoning Gym makes the task of creating and validating these prompts and tasks incredibly easy. To generate some propositional logic examples, you just call this reasoning gym.create dataset function. To prompt the language model to generate reasoning, we will first write this simple generation system prompt. Basically, we are asking the model to generate its thinking between these think tags and end with the answer tags. So the LLM is expected to output this XML format of a response. We will also write this extract function, which is basically doing some regex to extract the answers between those answer tags. To test, we loop through our reasoning gym dataset, extract the question, do some pretty printing here, and generate the LLM response. For now, we will just input it from the user's keyboard, and then we'll extract the answer from that response and use the score function that's also provided by Reasoning Gym to determine if the answer was correct or incorrect. So let's run that script to see what exactly happens. Okay, so that's our question, and above you'll also see our system prompt. We are going to manually type in the response for now, and bam, the score function says that our response is correct, so we get a +1 reward. If we rerun again and input an incorrect solution now, notice that the score function also correctly identifies it. Okay, so we have understood how the example generation and validation works. Now let's integrate a popular LLM like say GPT 4.1 mini from the OpenAI APIs to see what response that model generates. To do this, we replace the keyboard input prompt with an LLM generation function using this OpenAI's chat.completions.create function. Let's run this and see what happens. The LLM generates a solid response. We extract the answer from this XML with our little regex function and use the scoring function from Reasoning Gym to generate a reward. And seems like it's correct. Cool. So a large enough LLM can generate outputs without requiring additional few short examples or fine tuning. But how about a much smaller model like a 135 million parameter model, the small LM 135M instruct? Let's run this and see what happens. To load this model, we are using Hugging Face's transformers library, and we are calling this auto model for causal lm.from pretrained and passing in the model's name. And then instead of calling the openai.chat.completions API, instead we'll call this generate function where we're going to pass in the input IDs and the attention mask to sample a response from the LLM. And the model is generating incorrect responses because not only is its reasoning flawed, but it also isn't following the instruction of generating the XML in the right format. And that's causing us to not being able to even extract the answer to check if it's correct. So let's see if we can improve this behavior using reinforcement learning. And we will discuss this in the next section. So we have set up the environment. Next, we're going to set up how the actual RL is going to look like. But before that, let's draw out how the basic algorithm is going to look like before we dive into the code. GRPO works in two major phases: the experience collection phase and the training phase. During the experience collection, our current LLM interacts with the environment and fills up a buffer of experiences. What questions was asked, how it answered, and how the LLM was rewarded by the environment. And then after we have a record of these experiences, we're going to train the model. Here we will update our LLM to improve its responses such that it generates responses that lead to better rewards in the future. So let's now look at the experience collection phase in more detail. First, we sample a batch of questions from our environment. Let's say 2. Then we tokenize the prompts and send it to our language model and generate multiple responses from the language model. This can be done by probabilistically sampling different tokens by using a high temperature. Each response can then be detokenized back to a string response, and we can ask our environment to generate a reward score for each of the string responses. Answers that are correct and follow our requested format will get high rewards, while answers that are not will get low rewards. For each question, we get a diverse set of responses, meaning a diverse set of rewards, saying that indicates that some responses were good and some responses were not that good. Then from these rewards, we will calculate the advantages by standardizing the rewards with 0 mean and standard deviation of 1. Effectively, we are recording the relative advantages of each response with respect to other responses to that question. This step right here is why GRPO is called group relative, because for each group of responses for a question, we find the relative reward or advantage of each generated response, and we save these experiences into the buffer. One experience contains four things: the full sequence with the system prompt, the question, and the answer generated by the LLM, a binary response mask that tells us which of those tokens were LLM generated. Number three, the group relative advantage of the response. And lastly, the log probabilities of the generated tokens themselves. And we will see how exactly the log probs are going to be used in the next section when we discuss the training. Basically, in the training phase, we'll update our model's weights on the experiences we collected previously in the buffer. This is done by sampling a group of experiences from that buffer and maximizing the policy gradient objective using this equation. If you're feeling intimidated by these symbols, let me remove some stuff from here so it's easy to follow what's going on. Okay, that looks much simpler, and let's try to understand what these terms mean. The first summation is looping over all the generated responses in the group G, and the second summation is looping from t equal to 1 to the length of O, meaning it loops over all the tokens in each response. To recall, each question generates G responses, and each response has multiple output tokens. So these two summation operation is basically just a nested loop where you're going over each token one by one in your batch of responses. The 1 by G and the 1 by length OI basically converts the sum into a mean. Next we got this part, this pi theta times AIT. What does that do? Well, AIT is basically the advantage of every token. The easiest way to assign an advantage to each token is simply duplicating the advantage of the entire response. This means we are saying that every token is equally responsible for generating the correct answer. So if an answer got a +1 advantage, we are going to assign a +1 score to each token present in the response. So for that big group versus token matrix, this simple version of advantage will look like this. Lastly, what is this pi term? This whole term is basically the probability of each token with our current policy. It translates to what is the probability of the tth token in the ith response OIT when we input the question Q and autoregressively generate the past response tokens up to t-1 time steps. Cool. So now hopefully you've understood the complexity of these terms. To improve the language model's ability to solve the task, we need to maximize this term. But let's say you got two sequences, ABC and DEF. Let's say the environment scored a high value for ABC and low for DEF. And the advantage of ABC is +1 and DEF is -1. And these were the probabilities for each token. Well, when you multiply the advantages, the product becomes this. When you want to maximize this term, always remember that the advantages are fixed. They came from the environment, so you can't really update them because they are not parameterized. So to maximize these values, we can only change the probabilities coming out of the LLM. So increasing this expected score would mean to increase the probability of the tokens with a positive advantage and decrease the value of the tokens with negative advantages. Really think about that. To increase this objective, we need to update the model such that the log probs of the token that gave a positive advantage gets higher and those with negative advantages gets lower. And that basically means increase the probability of tokens that are generating high advantages and decrease those that are generating low advantages. Now that we understood things till here, we are going to add back some of the stuff that we had initially removed. First, the important sampling term here. Here, pi_old is the old policy network and pi is the current policy neural network. Basically, when we were collecting experiences during the exploration phase, we were using the pi_old policy that's in the denominator. And as we train the model on the buffer, its weights change, leading to a different policy network which we indicate as pi in the numerator. This important sampling ratio basically reweights the advantages between the currently training network and the old network which we initially used to collect those experiences. And this clipping term, it just ensures that the updates to the network does not become too large and the weights do not move way too far away from the old policy. It's basically a regularization term that says that you can increase the log probs of tokens that have high advantages or decrease the log props of tokens that have a low advantage, but don't make it too high. Don't change the weights too quickly, and that's why it claims that importance sampling ratio between 1 minus epsilon and 1 plus epsilon. If you still have questions, I will revisit this entire thing when I discuss the code. So hang on till then. As we train the model on this reinforcement learning objective, it's slowly going to increase the likelihood of generating tokens that lead to higher advantages, meaning answer things correctly. In the next section, let's see how to actually implement all of that in code. All right, so next, let's have a look at how we are actually going to do the GRPO fine tuning. I have a notebook here that sort of goes through all of the steps and explains it with some neat visualizations. So let's get started. So the first block here is just some normal stuff that you may have seen before in other tutorials. We basically load a model, and the specific model that we are loading is already fine-tuned on the syllogism task. So it's going to generate some positive rewards and some negative rewards. So that's going to help us to actually train the RL model and really understand the nooks and crannies of what exactly is going on. We need our network to generate some positive rewards as it's collecting experiences so that our RL optimizer can increase the probability of those positive rewards. So that's why I've already fine-tuned the model previously, and I'm using that to show off how GRPO works. Now let's load a single batch of training data and see how it looks like. So here you see we have a validator, which is basically our reasoning gym object that we're going to use to eventually assign rewards to the LLM's response. And we have the inputs. So let's see what the validator looks like. And here you see that we have two questions. All right. Question 1, question 2. We have two questions because up here we had set the batch size to 2, which means at each step we're going to sample 2 questions from the data loader. So we looked at what the validator is. Now let's look at what the input looks like. So if we did batch inputs is basically going to be a dictionary which contains the input IDs and the attention mask. If I look at what the input IDs, it is basically a tensor containing these integer tokens. Now, if I print out the shape of this, you're going to see it has the batch size of 2, which is the number of questions we had, and 285, which is basically the tokens after the question and the system prompt was tokenized. So if I just try to, decode, say batch inputs, input IDs, and let's say only the first one, here we are going to see what exactly the LLM is going to be prompted with. It contains our system prompt. It starts here and goes up till here, and then we start the user wherein we put in the question that we had sampled from our reasoning gym library, and finally we start the assistant response, and the goal is to pass this entire sequence into the model and then have it generate responses. So here this tokens here are just padding. And the reason we need to do this padding is because we want our tensors to be rectangular in shape. So even if the prompts of the 2 questions are of separate lengths, we are going to left pad them with the n token so that it's all rectangular and we can pass that into the LLM. And that's why if we look at the other thing present inside batch inputs, it is basically an attention mask. And that's a mask that tells the LLM the tokens that are padded and the tokens that are not. So you see in the second question, everything is 1, and the first question, you have 2 zeros, which indicates to the LLM to not give attention to those tokens when generating the response. Now in the next section, we are going to look at the collect experience function, where we basically are going to call this llm.generate function. And what that really does is it passes in the input IDs, the attention mask. It sets a limit of how many tokens that you want to generate. And here I have set it to 100, but you can increase it longer to give your model more thinking budget, allowing the model to think more before it generates the answer. The do sample equal to true allows the llm.generate function to randomly sample from the probabilities over all of the tokens in the vocabulary generated by the LLM. Now I said all of the tokens, but that's not true. because I set this top p equals to 0.95. If I had said top p equal to 1, it would sample from all of the tokens in the vocabulary. But when I set it to 0.95, it instead is going to sample from tokens that cover 95% of the probability mass. You can adjust this number to make your response more or less diverse. Next, we have the temperature, which basically adds a bias to the logits, making the probabilities of each token a little more distributed before the sampling occurs. So a higher temperature means a little more stochasticity, a little more diversity in the responses, whereas a really low temperature means that the highest probability tokens will likely get picked a lot more. The other interesting thing is this num return sequences parameter, which tells this LLM.generate function how many responses do you want to sample for each question in the batch. So let's see how all of that works. Let's just copy this part. Let's paste that here. Let's also copy at least that. Now this torch.noGrad, what that basically does is that everything that we do here, we are not going to calculate the gradients for this entire section, because remember, during the data collection phase, we are not really training or updating the model's weights, so we don't need access to its gradients. So we don't need to burn any compute trying to calculate the gradients at this stage. Later, when we are looking at the training section, we don't need to put this torch.noGrad there, because in that case we do need the gradients and we do need all the back propagation stuff. Anyway, so the full responses thing has run. Let's see what it looks like. And here you see that there are 6 responses and the total size is 383. Now what has happened is that we had set the n rollouts to 3 and we had 2 sequences in the batch, so that's why we have 6 responses in total. Next, if we did a tokenizer.batch decode of the full responses, you're going to see the responses that the model has generated. Let's also say skip special tokens equal to true, and let's also print out the first response. All right, so if we did that, first you see our system prompt. So up till here, it's the same as the input IDs that we had passed in. The answer begins from here. It has generated some thinking data and then it has generated an answer, and it has done this for all of the inputs. So if I print out the next one, you'll see that it has generated no here, and the third one it has generated yes. So for the first question, because we are doing this diverse sampling thing, you can see it is generating different responses, and soon as we are training, we are going to learn how to exactly train the RL module to increase the probability of the correct response. So let's go back to our experiences function. We have already seen what this does. It generates all of the responses. The next thing we do is to extract the assistant response. What this basically means is that we saw here that the input ID shape was 285 and the full response shape was 383. And this is because the response contains both the input IDs that we had sent in as well as the assistant part of the response. So to extract just the assistant part, we need to run this where input size is equal to this 285 number. So input IDs dot shape, and we'll take index 1. And so if we did a shape of this, it's 6,98. Awesome. If we did a tokenizer dot batch decode of this, and let's say print out the first one, and here you see that we have been able to extract just the assistant response part out of the full sequences. So now it just contains the response generated by the assistant, the thinking and the answer. So that's what I've done. I have taken the assistant response and done the batch decode to convert it into string. So if I run this as well, let's run this here. And then again, if I print out decoded response, it's basically a list of all of the responses that the LLM has generated. Again, remember the first 3 responses are for the first question and the next 3 responses are for the second question. Next, what we're doing is to calculate the reward for each of these responses. So let's see how we're doing that. Here we are passing in the decoded responses and we are passing in the validators. The validator we can find right there from the batch. And let's run that. So if we run that and then print out the rewards, it's going to look like this. Some of these are 1, some of these are 0.15, and if we did a reshape, it is basically going to show us the rewards per question. So for the first question we got a 1, a 0.15, a 1, and for the next question we got a 0.15, 1, and 0.15. Now the reason why some of the wrong answers also got a score is because we're also assigning a reward on the format of the answer. So if the answer contains all of the tags that we had asked for, the thing, the slash thing, the answer, and the slash answer tags, we're basically going to at least give it some reward. And in the end, we are going to weigh the format rewards and the correctness accuracy reward to come up with the final reward. So even if some of the answers are wrong, it's going to get a reward as long as it at least got the formatting correctly. So quickly, if I just extract the answer of, let's say, first decoded response, it was yes. So yes got a high score of 1. But if I do the next one, it was no, and that got a low score. All right, so hopefully that makes sense. So let's move on to the next part about calculating advantages. Here we are going to reshape the rewards. So if I print the rewards here and then also print the advantages, it is basically going to look like this. We are standardizing the rewards. So if we did an advantage dot mean, and let's say x is equals 1, it's going to be 0, 0, and if we took standard deviation, it's going to be close to 1. If you got a high reward, you're going to have a high advantage. If you got a low reward, you got a low advantage. Now interestingly, if you had every reward as 1, the advantage is still going to be 0, because in GRPO you're calculating advantages relative to other responses to the same group or the same question. And later on in the video, when I discuss the 10 practical takeaways from my experiments, I'm also going to make a mention of that case where every reward is 1 and the advantage is 0, and how to tackle such situations. All right, so we have the advantages here. The next thing that we're going to look at is this calculate logits function. What is that doing? Well, this one inputs the LLM, the full responses, and the attention mask, and calculates something called log props. Now what this basically is going to look like is our batch 6 and the shape 383. If I print this out, what's happening here? Let's print out the last 50 tokens of, let's say, the first example. All right, this. Now remember, our full responses 0, -50. So this shows the last 50 generated tokens for the first example. If I also do a decode of this, and let's say I loop over each value. All right, so these were the last 50 tokens, which is basically that, right? R is 359, and then humans is 2973. And these are the log props of that, meaning the confidence of the LLM when it generated those tokens. How is that actually calculated? Let's have a look at it here. All right, so the first thing that we do is passing the input IDs and the attention mask. If we run this code, we are going to get the raw logits of that response when we pass it through the LLM. You can see that the batch size 6, 383 is the sequence length, and 49152 is the vocabulary length, meaning the LLM could have chosen any of these 49152 tokens. Next, we do this log softmax operation. What that does is it applies a softmax operation onto those logits, meaning it makes a probability distribution of those logits that we had outputted and then take a log of that. So this whole thing just converts it into log probabilities. Finally, we do this selection operation where instead of keeping every token's probability in memory, like all of these 49,000 tokens, we just pick out the log props of the selected tokens. So that's what this is doing. So if I run that and print out the shape of this, this is 6,383. If you don't believe me, I'm going to show you what exactly had happened. Let's say we take the first batch and let's say we pick the 338 token. That's 511. And if we do a tokenizer.decode of this 511, it's basically all. So somewhere in the first response, the LLM had outputted the word all. Now, if we looked at the log props of every token that the LLM could have outputted for that token, we are going to look at like this, 0, 330. And what that's going to print is a long tensor. So if I print the shape of this, it's 49152 tokens. So these are all the tokens in the vocabulary that the LLM could have outputted. And we also have the access to every token, right? If you did a vocab or something, you're basically going to find the inverse mapping of every string token back to a token in the sequence. So these are basically the log props of every token inside the vocabulary. So if we picked out the 511 of that, that's going to give us minus 11, which is basically the log prob of that token all. So finally, if we did a selected log probs and do 0,330, it is that the same as the 511th token of that sequence. So hopefully that makes a lot of sense what this selected log probs thing is actually doing. It goes over all of the tokens in the batch, in the sequence, and picks out the log prob of the token that was selected at the time of generation. The higher this number, meaning closer it is to 0, the higher the probability of that number being selected. Awesome. So that's what is happening here. And in this final section, we are basically removing all of the paddings and saving an experience like this, where we have the input sequence, the log probability, the response mask, which if I show you what the response mask looks like, it is basically this mask that tells where did the LLM's response begin. So for response mask 0, you have this entire sequence that is marked as 0 because those were all coming from the system prompt, and the assistant response section is marked as 1. And the reason we are even storing this is because when we are updating the network's weights, we only want to focus our loss on the assistant section of the response and not the entire response sequence. All right, so in the next section, let's have a look at how the training is going to happen from all of the experience that we have just collected. Before that, do remember how the code is going to look like. First, we load all the models and all of the data loader stuff. And inside the main function, we collect a bunch of the experiences and then save it in a buffer. And when that buffer reaches a certain size, we execute the train function, replace the buffer with an empty array, and then we proceed again to exploration. If you look at the train function, all it really does is just randomly shuffle all of our experiences and then call this train on batch function to update the neural network's weight on a mini batch sampled from our experience buffer. Let's have a look at how exactly this train on batch thing is going to look like. So here, experience is basically one batch of data. Every experience contains the stuff that we had saved during exploration, which contains the input sequence, which actually contains both the input as well as the assistant's response. It contains the log probability of every token that was generated by the LLM. It contains the response mask. And finally, it contains the advantages, which records which of the responses has a higher reward compared to other responses from the same group. So at first we load all of them in, we left pad everything so that it is rectangular in nature. We calculate the current log probs of the LLM because as the neural network is going to be trained, the LLM's weights are going to update. So the original log probs we had during the collection of the experience is going to change because again, we are going to be updating the LLM's weights. So we are again calculating the log probs of every token in the sequence. And then finally, we pass that loss into the calculate GRPO loss function. I'm going to explain what the loss function does here in a bit, but for now, just assume that it calculates that advantage times log probability and all of the clipping stuff that we discussed earlier. And finally, we do accelerator.backward loss, optimizer step, and optimizer zero grad to make sure that we update the neural network's weight. So let's actually have a look and see if the loss actually updates as we run this block over and over. So the first time we run this block, the loss is 1.15. Let's see what happens if we run this again. We ran that again. You can see that it is decreasing. We run that again. The loss has decreased even further to 0.8. We run that again to 0.7. We run that again, 0.6. So hopefully you can see that with continued training, the loss indeed is decreasing. But what does it exactly mean to say that the GRPO loss is decreasing? What's happening under the hood is that we are raising the log probabilities of the tokens that generated a high advantage, and we are decreasing the log probabilities of the tokens that generated a low advantage. Let's see what the curve sort of looks like. I've written a simple matplotlib function here to show what it really means. So let's take index 4 and see how the log probs had changed after training. So for index 4, if we run tokenizer.decode, it looks like this. The important part starts here where the LLM responded yes. Look at the advantages of that. It was high, meaning the reasoning gym library generated a high reward for this response yes. So let's have a look at what the training that we did earlier caused. Here the orange bars are the old log probabilities, and on the y-axis we are printing out the last 25 tokens that the LLM had generated. So basically somewhere from here till the end. All right. And the orange bars shows the previous log probabilities when the LLM was in the data collection phase, when it was collecting experiences from the environment. And the blue line is showing the log probabilities after we did those 5 to 6 rounds of training on that batch. And you can clearly see that with optimizing with RL, the blue line has gotten further closer to 0. Again, remember this is log scale and we are on the minus x-axis here. And you can clearly see that the blue lines are shorter. So the training has raised the log probs of the positive advantage tokens, and that means it has more chances of being selected in the future. If we looked at one more example, let's say next one, maybe something with a negative score. Yes, so this one has a negative score, meaning the answer was likely wrong. And you can see that in this version, the log probs have actually decreased because the blue line is longer than the orange line, meaning these tokens are less likely to be selected in the future. So hopefully that sort of explains what this calculate loss and accelerate backward loss is actually doing. And next, let's have a look at this calculate GRPO loss function to really understand and hone in that policy optimization formulation and how to exactly implement it. All right, so here I am showing the advantages, all log probs, basically everything you need to know about that loss function in a table. We are specifically choosing an example where we have extremely high changes in the logits and see how it impacts the loss function. So here you have the all log probs of some of the tokens in that sequence as generated by the assistant. And you can see the ratio is quite large for some of these, like a lot has changed because of those train steps that we did. And that is what is captured in this ratio and the unclipped ratio. The clipped ratio, however, it basically bottlenecks it by saying you cannot move further than 0.2 from the ratio of 1. If I plot a different example, if the clipping ratio is in the range, so for example, here the ratio has remained the same, you can see that the clip ratio and the unclip ratio is the same. So clip ratio basically clamps the actual ratio between the new probabilities and the old probabilities between 1 minus epsilon and 1 plus epsilon. So we have epsilon as 0.2. So everything that is below 0.2 difference, like this one is 0.77. So it's more than 0.2 away from 1. You have the clip ratio as 0.8. Then you have the clipped loss and the unclipped loss. Well, the clip loss multiplies the clip ratio with the advantages and the unclip ratio with the advantages. So let's say if I did 0.6 multiplied by this, it's minus 0.977, and that's the unclip loss. Similarly, if I did for the clip loss, it's minus this, so that's the clip loss. So again, the clip loss and the unclip loss are basically just the product of those two things. And lastly, we calculate the minimum of these two things and treat that as our loss function. So the minimum of this and this is minus 1.13. So that is the term that we are going to minimize. Notice that because the advantage is negative here, our loss number here is positive. So if we decrease this number, it is effectively going to make this log props go lower. So if it is the product of the clip ratio and the advantages, we have the clip loss, right? And if we break it down even further, it's basically np.exp of the current log props, which is minus that, minus the old log props, which is this. So that's this number. So if we clamp this thing here, so np.clamp, let's say 0.8 to 1.2. Is it clip? So if we did np.clip and we clipped it between 0.8 and 0.2, let's also add the minus sign here. So now we have the loss. Now our goal is to reduce this loss, to reduce this number, but we can only change this value, this 16.25, which is the current log props. Because remember, the old log props are fixed when we sample them during our exploration, and the advantage is fixed as well because that comes from the environment. So if we decrease this number, let's say minus 18, for simplicity, let's remove the clipped stuff to really see what's happening. So we have this. Now, if we decrease this number from minus 16 to minus 18, we expect the loss to go down, and indeed it does. So if we keep decreasing this log prob, you can see the loss is going down, which basically means that because the advantage is low, we decrease the log probs, we see the loss go down. Now, what happens if the advantage was high? If we did that, then the loss is negative of that. So now if we decreased it, it actually increased the loss from minus 0.97 to minus 0.01. So the goal here would be to actually increase this number, increase the log probs, meaning if we increase it to, let's say, minus 4, we actually have a lower loss now. Now in this particular case, you saw the loss can explode. This is a very high number, and that is the reason we have this clip thing. Because if we added back the clip thing again, let's do that quickly. 0.8, 1.2. Here the clipping thing is actually coming in clutch, and it's reducing how much the network can change. So instead of that really high number, you're basically scaling the advantage by just 1.2. And so that's what's happening here. Like for some cases, the clipping ratio is really limiting how much the network can actually change. So all right, so that's kind of a description of how the policy gradient function works like. Again, always remember, this sign is very confusing. Our goal is to reduce the loss, meaning to increase that advantage times log probability matrix. So if the advantage is negative, our goal is to actually decrease this log props value. And if the advantage is positive, our goal is to increase the log props value. So hopefully that sort of made a lot of sense to you. In the next section, we are going to look at supervised fine tuning and how a little bit of supervised data can really improve how RL agents can train on reasoning tasks. RL trains by collecting experiences and updating the policy to maximize the good experiences. But if most of the experiences are completely bad, the model receives 0 rewards all the time, it is no way to optimize because it gets no signal to improve at all. So the recommended approach for small models is to first teach the model the behavior you want to train using supervised fine-tuning. You can find the details of supervised fine-tuning in my fine-tuning video right here. I explained it step by step in that video, so I won't repeat myself here, but I will go over some of the main points. To generate the fine-tuning dataset, I first generated some text with a small LLM like GPT 4.1 Mini using an OpenAI API. Then I attached a trainable LORA adapter to the base model and did the supervised fine-tuning. LORA, or low rank adaptation, is a fine-tuning technique where we attach new weights to the base model and only update the new weights to learn the training data while keeping the base model's weight fixed and frozen. This allows the training process to be more memory efficient and also reduces the risk of corrupting the original model. Again, I go over all of this in that other video, which I will be sure to link in the description below. This is how you would define a LoRa config and attach it to the base model. We load our dataset from our generated JSON-L file, loop through it, input the tokens, retrieve the loss, and update the weights. Hugging Face's Transformers library does most of the heavy lifting for us by calculating the loss inside the model's forward pass itself, so even less code for us to write. I trained a LoRa adapter on about 200 examples of the syllogism task and the smallest language model I could find, the small LM 135 million instruct model, and it got an accuracy of around 45%. Roughly, this means that we generate a correct answer 45% of the times. Let's see how GRPO does now, when the model is slightly more advanced and can output things in the right format and sometimes even correctly. From the rewards curve, you can see that the model indeed sees more rewards up front, and there is a general upward trend in the rewards as we continue the training. By the end, we get an accuracy of 61%, which is really exciting. Again, remember that the RL phase does not provide any direct input or any direct signal on how to reason. It just looks at the final answer and tells it if it's good or bad. And then RL and all of the advantages and all of the, like policy update thing, that takes care of the rest. It's brilliant. I also repeated this experiment with slightly larger models like the 360 million instruct and the Quen 3.6 billion model. In the latter, I was able to get accuracies for up to 81%, which is just awesome. We consistently got a 20% additive bump on average with the syllogism task. In the propositional logic task, which in my opinion is a harder reasoning task, I also saw similar gains across all small models. I'm sure that with more instruction tuning and longer RL fine tuning, preferably on multiple tasks at once, we can raise the intelligence of these models a lot higher. Training on a single task can generate quick results, which is what I wanted for this YouTube video, but it can also act as a bottleneck for the model's overall intelligence. So maybe in the future, I am going to train on multiple tasks at once and see if I can beat these scores. I will let some of the footage play of the new thinking models and the outputs that it generates. It's pretty awesome to just stare at these and just marvel that this is even possible. I personally don't believe in any of these, that this is actually happening, but that's the magic of RL. It's very hard to train. It's very frustrating to train sometimes, but when it works, it feels euphoric. In this final section, I'm going to list 10 things to keep in mind when training reasoning models, especially on small language models. Number one, not all reasoning tasks can be solved by all models. Small models don't have as much world knowledge that the large models, say above 14 billion parameters, do. An easy way to verify if a task is too hard or too easy for the model is to just check the base accuracy of the model on your own task. If it is, let's say, below 10 to 20%, the task is likely very hard and you need additional supervised warm-up fine-tuning. Number two, SFT, even on small data sets, can generate massive gains in accuracy on small models. If you can acquire a good data set or generate one, you may not even need to do RL in many scenarios. SLMs are immensely tunable. Number three, reasoning research is still an evolving field. In the original DeepSeek math paper that introduced GRPO, the researchers noticed that as training goes on, the model outputs get more and more long. And they saw this as an indication for the model's evolving intelligence. But follow-up research papers like the DAPO and the critical perspectives on R1 have challenged this idea to introduce new normalization terms into how losses are aggregated. And apparently these losses can mitigate the length bias issues in the original GRPO formulation. I tried all of those loss functions as well and experimented with them, but for my rather simple task, the vanilla GRPO loss just worked perfectly. But it's good to keep these losses in mind for more future experiments. The DAPO paper also mentions to remove the KLD term in the original R1 paper. You may have noticed I did not even mention this term in the loss function of this video. See, in the original GRPO paper, the goal of this loss was to ensure that the updating policy is never too far away from the base policy. But DAPO suggests to not use this because the behavior of the policy can drastically change during reasoning, making this KLD term an unnecessary regularization constraint that will restrict the model's future intelligence. Number 5, generating diverse responses is key to make RL possible. If you generated correct responses always or incorrect responses always, the advantage will be 0, meaning when calculating the product between the advantages and the log props, they will also be 0 and not give you any training signal at all. Generating diverse responses with diverse rewards makes it possible to train RL in a contrastive way where you can tell the LLM what's good, what's bad. So if you're training RL models, log out those rewards and track the standard deviation. If you see the standard deviation is low, meaning the responses and the rewards are not diverse enough, you can either introduce more reward terms or you can increase the temperature of the generation to make the outputs more random, or the number of generated sequences to have a wider sample set. 6. To remove useless examples from your experiences, you can remove experiences that have close to zero advantages altogether. This is another optimization mentioned in one of those papers. There are new papers coming out every day on this, and they are finding more and more about reasoning and optimization, from updating the clipping loss to be asymmetric to adding penalties for extremely long generations and reward shaping. So be on the lookout and stay close to the literature. 7. The following parameters increase the stability of training at the cost of compute: increasing number of generations per rollout, size of the buffer, lowering the learning rate. Number 8. Have a close look at your SFT dataset file. For example, just adding white spaces between your answer tags will make the tokenization process simple and consistent throughout, making the learning task much easier for your LLM. 9. Your system prompt is often forgotten in all of this. You can add more instructions to make small models follow instructions more closely. You can also add few short examples in the prompt itself to further guide the training. Number 10. RL is finicky, especially with policy gradients. As your network starts to improve, it is going to generate positive rewards for most questions, especially if your task set is small and limited, which was the case for my experiment. So it is important to add inferencing at regular intervals to capture the best model state. Otherwise, with long training, the model might begin to oscillate without showing any progress, because as mentioned previously, when all the rewards start getting high, the advantages are less well distributed, leading to low gradients. Annealing the learning rate, setting the clipping ratios low, and even adjusting the LORA parameters will ensure that the model is training stably enough, especially in the final stretch of the training. So if you regularly inference during the training process, there's a high chance that you'll be able to catch the best state of model that performs well in an unseen test set. And that's it. These are some of my takeaways from this reasoning project. I hope to see you soon in the next video. Remember to hit the subscribe button and leave a like. Check out our Patreon page, where I will be uploading all the materials I used to produce this video. Follow me on my X account for continuous updates on my next projects. I will be seeing you soon. You're magnificent.